Hello, today we're talking about how to code up a transformer from scratch. I'm gonna skip the import part. I have commented on some of the relevant information here that you can read. So first we create a dictionary that maps vocabulary tokens to ID numbers. And then we create a dictionary that maps the IDs to token. This will help us interpret the output. We use the map function to apply the reversed function to each tuple stored in the token to ID dictionary. And we then use dictionary to make a new dictionary from the reverse tuple. And here we have two inputs. What is AIPI? Awesome. And AIPI is what? Awesome. So because we are using decoder-only transformers, the outputs or the predictions are the input question minus the first word followed by end of sentence. Awesome, end of sentence. The first end of sentence means that we're done processing the input question, and the second EOS means we are done generating the output. And now let's package everything into a data loader. D model equals to the dimension of the transformer, which is also the number of embedding values per token. Max len equals to maximum number of tokens we allow as input. Since we are pre-computing the position encoding values and storing them in a lookup table, we can use D model and max len to determine the number of rows and columns in that lookup table. We're only using the short phrase. AIPI is what? Awesome. So we are using max len equals to 6 as the default setting. Here we're calling the supers init because by creating our own init method, we overwrite the one we inherited from an module. So we have to explicitly call an modules init, otherwise it won't get initialized. Now we create a lookup table, PE, of position encoding values and initialize all of them to 0. To do this, we will make a matrix of zeros that has max len rows and D model columns. Now we create a sequence of numbers for each position that a token can have in the input or output. Here I have created a custom arrange function where we calculate the number of elements first and then create an array using a list comprehension, then convert it to desired data type. Here the unsqueeze1 converts the single list of numbers that custom arrange creates into a matrix with one row for each index and all of the indices in a single column. Now let's create an index for the embedding position to simplify the code a little more. And now we calculate the actual positional encoding value. Here I created custom sine and cosine and initialized the PE as a matrix of zeros with max len, maximum number of input tokens, rows, and D model number, which is number of embedding value per token columns. And here we register PE. Register buffer basically ensures that PE will be moved to wherever the model gets moved to. So if the model is moved to a GPU, then even though we don't need to optimize PE, it will also be moved to that GPU. This in turn means that accessing PE will be relatively fast compared to having a GPU have to get the data from a CPU. And because this class position encoding inherits from an ninja module, the forward method is called by default when we use a position encoding object. In other words, after we create a position encoding object, PE, position encoding, then we'll call the forward function, and then where we will add the position encoding values to the embedding values. And here the D model is the number of embedding values per token. Then we initialize the weight that we will use to create the query, key, and value numbers for each token. I have also created a custom linear function where I initialize the weights and biases, then with uniform distribution. Then I perform the linear transformation. In the forward method, we created the query, key, and values using the encoding associated with each token. and then compute the attention score, which is the equation listed here. And then I sort of created a multiplication of matrix function, which I won't go into too much detail. Here we're masking out things we don't want to pay attention to, like tokens that come after the current token. We replace pad or tokens that come after the current token with a very large negative number so that the softmax function will give all masked elements an output value, or a probability of 0. And then we apply the softmax to determine what percentage of each token's value to use in the final attention values. Then we scale the values by the associated percentage and add them up. In this example, the AIPI example, we're just using a single layer decoder. If I guess if we wanted to use multiple layers of decoder, we would take the output of one decoder module and use as input of the other. And then the forward method, basically for the decoder only transformer, we need to use masked self-attention so that when we are training, we can't cheat or look ahead at words, come after the current word. To create the mask, we are creating a matrix where the lower triangle is filled with 0, and everything above the diagonal is also filled with 0. We then replace the zeros above the diagonal, which represent the words we want to be masked out with true, and replace the ones in the lower triangle, which represent words we want to include when we calculate self-attention for specific words, and the output with false. Lastly, we configure the optimizer, simply passes the parameter we want to optimize to the optimize and sets the learning rate. And then training step is called by Lightning Trainer when we want to run the training, want to train the model. Now, first we create a model from decoder only transformer. Now we create the input for the transformer. Then we get the prediction from the model. And we flatten in the argmax function, which I guess coded up from scratch, and not sure if we have enough time to go through it because of the time constraint, but we'll store the predicted ID in an array that we will add to each time we predict a new output token. And now use a loop to predict output tokens until we get an end of a sentence token. This is also a concatenate function that I have coded up from scratch. Basically checks if all the tensors have the same shape except for the concatenation dimension, then determine the shape, initialize the result, and then concatenate. So here, if the prediction is end of sentence, then we're done. And yeah, basically this is what I described earlier for the loop. And now print out the predicted output phrase, end of sentence, and then set to 42, yay. And here, now we're actually training the model. You can see that, that it has been completed. And let's test it. Here, we're testing what is AIPI, and we got awesome. Then we're done. And here, AIPI is what? We also got awesome. So yeah, thank you very much for listening.